300 million light-years away, in a galaxy nobody had ever bothered to name, something woke up. For 20 years, telescopes scanned past it without stopping. It was just another smudge of light in the constellation Virgo, a galaxy with no distinguishing features, no violent history, nothing worth a second look. Astronomers call galaxies like this boring, and for 2 decades that's exactly what it was. Then, in December of 2019, it stopped being boring. Without warning, the center of this galaxy began to brighten. Not gradually, abruptly. A patch of sky that had been quiet for as long as anyone had been watching started glowing with new intensity, as if someone somewhere had flipped a switch. Astronomers had a guess about what was happening. Deep in the heart of nearly every large galaxy sits a supermassive black hole, an object so dense that light itself cannot escape it. Most of the time, these black holes are quiet. They sit in darkness, starved, waiting. But every so often, one of them stirs. It begins pulling in gas and dust from its surroundings, and as that material spirals inward, it heats up and radiates, turning a sleeping giant into what astronomers call an active galactic nucleus. That's what this looked like, a black hole waking up. But then in February of 2024, something happened that no one had a name for. The black hole began flashing, not randomly, rhythmically. Every 4.5 days, almost like clockwork, an enormous pulse of X-rays would erupt from the center of the galaxy, blaze for roughly a day and a half, and then fade. Then 4.5 days later, it would happen again, and again, and again. Scientists have seen black holes flare like this before. They call the phenomenon a quasi-periodic eruption. But nothing like this. These eruptions were 10 times brighter than any quasi-periodic eruption ever recorded. They lasted 10 times longer. Each single flash released roughly 100 times more energy than similar events seen anywhere else in the universe. And buried inside that 4.5-day rhythm was something even stranger, a slower, deeper pulse, repeating roughly every 25 days, as if 2 separate clocks were ticking inside the same black hole. Why would a black hole that had been silent for 20 years suddenly begin pulsing with this kind of precision? What could produce flashes this powerful, this regular, and this large? And why did the object that seemed to be causing them show no sign of the one thing that usually explains eruptions like this, a star torn apart and consumed? Astronomers didn't have an answer. They still don't, not completely. But over the past several years, they've been building one, piece by piece, watching in real time as a supermassive black hole does something no one has ever caught it doing before. This is the story of that black hole. Astronomers gave it a name, Ansky. Today we're going to follow this discovery the way the scientists themselves experienced it, or sign Hurstarsatitser, not knowing the ending in advance. We'll start with what a sleeping black hole actually is, and why most supermassive black holes spend the vast majority of their lives doing nothing at all. We'll look at how Ansky was first noticed, almost by accident, by a survey telescope scanning the sky for anything that changed. We'll follow the years of quiet monitoring that came after, as astronomers tried to figure out whether what they were watching was truly a black hole switching on, or something else entirely. Then we'll get to the eruptions themselves, the 4.5-day flashes that shouldn't have been possible, and the competing explanations scientists have proposed to explain them. We'll examine the leading theory, the object that seems to be missing, and the evidence that has forced astronomers to reconsider what quasi-periodic eruptions actually are. Finally, we'll look at where this investigation stands right now, what's confirmed, what's still just a guess, and why a distant, previously boring galaxy might end up teaching us something new about how the universe's most extreme objects behave. To understand why Ansky is so strange, you first need to understand what a supermassive black hole is doing most of the time. And the answer for the vast majority of black holes is nothing. Nearly every large galaxy, including our own Milky Way, has one of these objects sitting at its center. They range from hundreds of thousands to billions of times the mass of the Sun, compressed into a region of space that, relative to their mass, is almost unimaginably small. The one at the center of the Milky Way, called Sagittarius, a star, is about 4 million times the mass of the Sun. You might expect an object like that to be constantly devouring everything around it, growing more violent by the day. In reality, it's the opposite. Supermassive black holes spend most of their existence in a dormant state, quietly starving. There simply isn't much gas and dust close enough in the right orbit to fall in. Without fuel, a black hole doesn't radiate. It doesn't announce itself. It just sits there, invisible except for its gravitational influence on nearby stars. Every once in a while, that changes. A cloud of gas drifts too close. A passing star gets torn apart by tidal forces. Some disturbance sends material spiraling inward, and as that material falls toward the black hole, it doesn't go quietly. It forms a swirling accretion disk, compresses, heats to millions of degrees, and begins to glow across the electromagnetic spectrum, from radio waves to X-rays. When that happens, astronomers say the black hole has become an active galactic nucleus, or AGN. It's now one of the most energetic objects in the universe, capable of outshining every star in its host galaxy combined. Most active galaxies we observe have already been active for a long time, thousands or millions of years from our perspective. Even if the light left them long before human civilization existed, we arrive after the transformation is already complete. What astronomers had never actually witnessed, not once in the history of the field, was a black hole making that transition, the moment of waking up, the turning on. That's what made the galaxy known as SDSS 1335 plus 0728 so remarkable. For the first time, astronomers weren't looking at an active black hole. They were watching one become active in something close to real time. The galaxy itself has a catalog name that only an astronomer could love, SDSS 1335 plus 0728, a designation from the Sloan Digital Sky Survey marking its position in the sky. It sits roughly 300 million light-years from Earth in the direction of the constellation Virgo, close by cosmic standards, but utterly unremarkable in every survey that had ever looked at it. That changed in December 2019, when the Zwicky Transient Facility, a wide-field camera in California designed to scan huge patches of sky night after night, looking for anything that changes, flagged the galaxy's nucleus as suddenly, significantly brighter than it had been. The event was logged with its own transient designation, ZTF19ACNSKYY, which is where the nickname Ansky would eventually come from. At first, this brightening alone wasn't unusual enough to draw much attention. Galaxies flicker for all kinds of reasons. A supernova near the core, a passing burst of star formation, even a random alignment of foreground light. But this brightening didn't fade. It persisted. Month after month, then year after year, the nucleus of SDSS 1335 plus 0728 continued behaving like an active galaxy that simply hadn't been active before. Astronomers led by Lorena Hernandez Garcia at Chile's Universidad de Valparaíso began following it closely. They pulled archival data from the eRosita X-ray telescope and requested new observations from NASA's Swift Observatory, trying to see whether the object was emitting X-rays, the classic signature of hot gas falling into a black hole. At first they found nothing, no X-rays, just a steadily glowing, increasingly active-looking nucleus with none of the high-energy signature they expected. Then, in February 2024, that changed abruptly. X-ray telescopes began registering something new, rapid, powerful bursts appearing and vanishing on a scale of days rather than years. Astronomers pointed additional instruments at the galaxy. NASA's NISR telescope aboard the International Space Station, the Chandra X-ray Observatory, and ESA's XMM Newton, one of the only instruments sensitive enough to measure not just the bright flares but the faint emission in between them. What they found was a black hole caught mid-transformation, quiet for 20 years, gradually brightening for 5, and now suddenly pulsing with X-ray flares unlike anything cataloged before. They gave the active nucleus its nickname, Ansky, and the investigation began in earnest. To understand why Ansky puzzled scientists so deeply, you have to understand what a quasi-periodic eruption normally looks like, and why Ansky broke almost every rule. Quasi-periodic eruptions, or QPEs, were first identified only a few years earlier, and by 2024, astronomers had cataloged fewer than a dozen confirmed examples across the entire observable universe. In every previous case, the pattern looked roughly the same. A supermassive black hole, already sitting at the center of a galaxy, would periodically flare in X-rays, bursts lasting perhaps an hour, recurring every few hours to a day, each one releasing a modest, if still enormous, amount of energy. The leading explanation for these events involved a smaller object, a star, a stellar remnant, even a smaller black hole, caught in a tight orbit around the central supermassive black hole. As that smaller object swung through the black hole's accretion disk again and again, it would slam into the surrounding gas twice per orbit, generating shock waves that heated the material and released bursts of X-rays. Picture a skipping stone crossing a pond over and over, sending out ripples each time it touches the surface. That mental picture became the working model for QPS, a small body repeatedly disturbing a disk of hot gas around a larger black hole. It was an elegant idea, and it fit the handful of known cases reasonably well. Many of the known QPE sources also showed evidence of a tidal disruption event, an episode sometime in the past, when the central black hole had torn apart and consumed an unlucky star. That connection made sense, too. A shredded star could leave behind exactly the kind of debris disk needed to produce these shockwave flares. So when Ansky's eruptions began, the first hypothesis on the table was the obvious one. Astronomers expected to find a smaller object orbiting through freshly formed debris, likely the remains of a star the black hole had recently destroyed. There was just one problem. When they looked for that debris, they couldn't find it. If Ansky's eruptions came from the same mechanism as every other known QPE, there should have been telltale signs of a torn-apart star, a specific pattern of fading in optical and ultraviolet light, a burst of emission consistent with stellar debris, some direct evidence that a tidal disruption event had occurred in the years before the X-ray flares began. Astronomers went looking. They checked the years of optical and ultraviolet monitoring collected since the galaxy first brightened in 2019. They examined the archival e-Rosetta data, the observations that had shown no X-ray emission at all between 2020 and 2023, and the swift observations taken between 2021 and 2023, which likewise showed nothing. Whatever was happening at the center of this galaxy, it did not carry the fingerprint of a shredded star. That absence mattered enormously. Every other confirmed QPE source had some connection, direct or suspected, to a tidal disruption event. Ansky had none, and that wasn't the only way it broke the mold. The scale of the eruptions themselves was, by every measure, extreme. Typical QPS release bursts that might last under an hour. Ansky's eruptions lasted roughly a day and a half, and Stursitz's about 10 times longer. Typical QPS recur every few hours. Ansky's recurred every 4.5 days, the longest cadence ever measured for this kind of event. And in terms of raw energy, each of Ansky's eruptions was pumping out roughly 100 times more energy than a typical quasi-periodic eruption elsewhere in the known catalog. Then there was the second rhythm, the one hiding beneath the obvious one. Layered on top of the 4.5-day flashes, astronomers detected a slower modulation, a super period repeating roughly every 25 days. It was as though the eruptions themselves were breathing, growing stronger and weaker on a longer cycle, even as they kept their faster 4.5-day beat. None of the existing models built to explain ordinary QPEs could easily account for all of this at once. Astronomers had a genuine mystery on their hands. Eruptions 10 times bigger, 10 times longer, and 40 times slower in cadence than anything previously known, coming from a black hole with no evidence of the one ingredient. A devoured star, that was supposed to explain the phenomenon in the first place. If Ansky's eruptions weren't caused by a black hole feasting on the debris of a torn-apart star, then what was producing that steady 4.5-day heartbeat of X-rays? Researchers turned back to the one piece of information they did have with confidence. This was a newly forming accretion disk. Remember, SDSS 1335 plus 0728 had been essentially dormant for 2 decades before December 2019. Whatever was now surrounding the black hole, it hadn't been there for very long, at most a handful of years. That gave scientists an alternative explanation, one that didn't require a destroyed star at all. Instead of assuming the disk was made from stellar debris, they proposed that the black hole might simply be accumulating gas directly from its surroundings, ordinary interstellar material, slowly gathering into a disk as the black hole switched on for the first time in this observing era. If a smaller object, perhaps a star, perhaps a compact remnant, orbiting undetected around the central black hole, happened to pass through this freshly forming disk on a regular orbit, it could produce exactly the kind of repeated shockwave heating that generates QPEs without needing a tidal disruption event to explain where the disk came from. This reframing mattered more than it might first seem. If correct, it means quasi-periodic eruptions aren't exclusively tied to stars being torn apart. They might also arise naturally whenever a black hole forms a new accretion disk and something happens to be orbiting nearby when it does. In other words, Ansky wasn't breaking the rules of QPEs. It was revealing that the rules were incomplete. But even this explanation left major questions unresolved. What precisely is orbiting through Ansky's disk to produce the shock waves? Why is the disk itself so much more energetic than expected, capable of producing flares 10 times more luminous than any seen before? And what's driving that mysterious 25-day superperiod layered underneath the faster rhythm? Is it the shape of the disk itself, a second orbiting object, or some interaction between the disk and the black hole's own rotation? Every answer researchers found seemed to generate at least one more question. It's worth pausing here to separate what has actually been observed from what remains interpretation, because in a discovery this new, the line between the two is doing a lot of work. What has been directly observed is not in dispute. The optical brightening beginning in December 2019, confirmed by the Zwicky Transient Facility, 5 years of persistent AGN-like variability that followed, the complete absence of X-ray emission through 2023, confirmed independently by both Erosida and Swift. Then beginning in February 2024, powerful recurring X-ray bursts, measured in exquisite detail by Neisser, Chandra, and XMM Newton, with a roughly 4.5-day cadence and a longer 25-day superperiod layered on top. All of this is solid, repeatedly confirmed observational fact. What remains hypothesis is the mechanism. The idea that a smaller object is orbiting through a newly formed accretion disk, generating shockwave-driven flares, is currently the leading explanation among the researchers who discovered Ansky, but it hasn't been directly confirmed. No one has directly detected the orbiting object itself, if one exists. Researchers are inferring its likely presence from the rhythmic pattern of the eruptions, the same way astronomers infer a planet's existence from the regular wobble it produces in its star, without seeing the planet directly. Other researchers studying the same dataset have offered refinements and alternative angles. Some analyses of the Neisser observations have focused on the possibility that the 4.5-day timescale itself may not be perfectly fixed, that it appears to have doubled or shifted over the course of continued monitoring, which would suggest the geometry of the system is still actively evolving rather than settled into a stable orbit. That's an important distinction. A young, still-forming disk behaving somewhat chaotically is a different physical picture than a smaller object locked into a clean, stable orbital rhythm. There's also genuine scientific interest in what Ansky might mean for gravitational wave astronomy. Researchers involved in the discovery have pointed out that interactions of this kind, a smaller object repeatedly disturbing material near a supermassive black hole, are also expected to generate gravitational waves, the kind that future missions like ESA's planned LISA observatory, a space-based gravitational wave detector, could potentially detect. If that connection holds, events like Ansky's eruptions could eventually be studied through two completely independent channels, the X-ray light we see today and gravitational ripples that a future mission might one day catch directly. None of this amounts to disagreement in the adversarial sense. It's the normal, healthy uncertainty of a genuinely new field where a single spectacular object is forcing researchers to build the framework and test it in real time, rather than fitting new data into an already settled theory. So where does that leave us right now, in the summer of 2026? Astronomers are confident that SDSS 1335+0728 represents the first supermassive black hole ever observed transitioning from complete dormancy into an active state, tracked continuously from the very first sign of brightening through years of follow-up monitoring. That alone makes it a landmark case study. A Rosetta Stone for understanding how galactic nuclei switch on. They're similarly confident that the X-ray eruptions beginning in February 2024 are genuine quasi-periodic eruptions, but ones that are extreme outliers compared to every other known example, roughly 10 times more luminous, 10 times longer in duration, and with by far the longest recurrence timescale ever measured, all layered with an unexplained 25-day superperiod. What remains genuinely uncertain is the precise mechanism producing those eruptions. The leading hypothesis, a compact object interacting with a newly formed accretion disk, rather than the debris of a destroyed star, Norris Auris in Sau, or Sauer, Nurisauer, or de Dursauer, currently fits the available evidence better than any alternative, but it hasn't been proven. and details like the apparently shifting cadence suggest the system may still be settling into whatever stable configuration it will eventually reach, if it reaches one at all. Continued monitoring is the only way forward. Every additional eruption gives researchers another data point to test whether the 4.5-day and 25-day rhythms hold steady, drift, or break down entirely. Future X-ray missions, along with the eventual arrival of gravitational wave observatories sensitive enough to catch signals from exactly this kind of system, may eventually let scientists confirm or rule out whether an unseen object really is orbiting inside Ansky's disk, and if so, what it actually is. For now, Ansky remains something rarer than a solved mystery, an active one, unfolding in real time, with astronomers around the world watching the same object, waiting for its next flash. There's something worth sitting with in the fact that this discovery was even possible. For most of the history of astronomy, black holes were theoretical curiosities, mathematical consequences of Einstein's equations that nobody expected to observe directly. Then gradually, evidence accumulated. Stars orbiting an invisible mass at the center of our galaxy, event horizons imaged for the first time, gravitational waves detected from black holes colliding across the cosmos. Each discovery answered a question that had lingered for decades. Ansky is different. It isn't answering an old question. It's revealing that we didn't know enough to ask the right one. Before 2019, no one had a framework for what a black hole waking up would actually look like in real time because no one had ever caught it happening. The models astronomers built for quasi-periodic eruptions were based on a small handful of examples, all of which shared certain features, because that's all anyone had ever seen. Ansky simply didn't fit inside that box, and rather than force it to fit, researchers are letting the object teach them what the box was missing. That's what real scientific investigation looks like, not a straight line from question to answer, but a slow, careful process of noticing when the universe refuses to behave the way your models predicted, and having the patience to figure out why. 300 million light-years away, the light we're seeing left that galaxy long before humans existed. Whatever is happening around that black hole right now, in the present moment on the other end of that light's 300 million-year journey, we won't know about for centuries. All we have is this delayed signal, arriving now, of a supermassive black hole in the middle of transforming itself, pulsing every 4.5 days, breathing every 25, still not fully understood. It's a reminder of something easy to forget. The universe doesn't wait for us to have the right theory before it acts. It simply happens on its own timescale, indifferent to whether we're watching. We just happen to be watching this time, cameras pointed at an unremarkable patch of sky, at the exact moment something remarkable began. Somewhere out there, right now, another black hole might be starting to stir. We won't know until the light reaches us, and when it does, we'll be ready, because of what Ansky taught us about how to look.